So, hello everyone. Welcome to the Recurrent ETDS seminar. So today, to our pleasure, we have Daren Wei from National University of Singapore, and both me and Shilpakda have shared time with Daren at Hebrew University and at Penn State, I guess. So it's a pleasure to have him talk about his recent work on time changes rigidity for unipotent flow. So over to you, Darren.
Okay, thanks. Thanks for the introduction, Nishan, and thanks a lot for the invitation from Nishan and Shilpak. And it is a pleasure to meet everyone and see everyone. I'm very happy to see all of you again. Okay, so today my talk is about the time change rigidity for unipotent flows, and everything is a joint work with Elon Lindenstrauss. Okay, so let's start from some uh, basic notions. So this is because this title of this seminar is ergodic theory and the dynamic systems seminar. I would like to assume that everyone know what is ergodic. So, but we still make all these kind of settings becomes clear. So the basic setting is that we always suppose that we are working with a standard probability barrier space, and our system is a measure preserving ergodic flows. And another notion is closely related, to our project in some sense is that the isomorphism relation. So if we have two ergodic measure preserving flows, we say they are isomorphic, and we use this notation here to define this for simplicity. If for every t belongs to R, we have a measure preserving transformation per psi from x to y, which is invertible almost everywhere, such that this relation holds. One of the most important part of this relation is that to say that the time t iteration for capital T exactly stands to the time t iteration for the flow as capital ST. This is the most important feature of the isomorphism relation. And this can be demonstrated through this picture. So roughly what this isomorphism relation tells us is that if x is sent to the psi x, then for tt1x, it will be exactly sent to the st1 psi x. And same thing for tt2, tt3, and tt4, and so on and so forth. So you see that the trajectory essentially exactly sent to the corresponding point's trajectory with exactly same iteration amount. And this is the feature of the isomorphism. And I will explain to you later why this is very important for us. Okay, but once we have this isomorphism relation and we have ergodic flows, it is very nature to think about, okay, can we do some classification? Based on for this isomorphism relation. Well, this in fact is the starting point of the theory of the entropy. This should go back to the Kolmogorov and Sinai when they invented this measure theoretical entropy. And the starting point is that how can we distinguish two different Bernoulli shapes, which is two 1/2 and 3 1/3. And the reason they are not isomorphic, measurable isomorphic, because one of them, the entropy is log 2, and then another is a log 3. And then once we have this, as I said before we mentioned this example, we want to understand, okay, whether it's that possible we can do some classification or based on some certain invariant or by something. And luckily by Austin theory, all Bernoulli shifts of the same entropy are measurable isomorphic with each other. So that essentially means if we want to do the classification for the Bernoulli shifts, the only thing we need to do is just compute its entropy. And entropy tells us everything up to isomorphism equivalence among the Bernoulli shifts. This is very nice. And right now, let's say something I like to say very similar to this kind of equivalence, how to say this, very nice thing for this, I like to say, as isomorphic equivalence relation. Also, in some sense, show some certain something. So as you can see in the title of today's talk, I mean, there is some word of the rigidity and the unipotent flows. And right now we have this isomorphic equivalence relation. So let's talk about what is rigidity and what is unipotent flows. So right now I will explain the very famous result by Marina and Ratner. So the citing will be the following. So GI is a connected semi-simple Lie group. And the small gi, this frac gi, is the corresponding Lie algebra. And the gamma I is the lattice, such that the gi acts physically on gi modulo gamma I, which means that we do not want to say some central elements. Okay? And the ui is just an element such that the joint ui is nilpotent. And in this way, we will make by taking the exponential, its corresponding element in the Lie group will be the unipotent element. And additionally, we assume that UTI acts ergodically on GI modulo gamma I, and where this UTI is a flow induced by this element. And MI in this kind of our consideration will always be the probability measure defined on GI modulo gamma I induced from the Haar measure GI. This is a setting. And why I would like to say this is a very classical setting, because due to Marina Ratner's later, the very famous result of the major classification, which is something we are not talking in today's talk. But due to the major classification result, her major classification result, this kind of setting essentially contains, the major cases for the unipotent flows on semi-simple Lie group. Okay, so right now let's mention the result I want to talk, which is closely related to today's our main theory, which is isomorphic rigidity for unipotent flows. And this is a result due to Ratner and Vitti, and which is Vitti-Morris. And it says that if UT is isomorphic to UT1 is isomorphic to UT2 through per psi, it's just a measurable isomorphic at the beginning assumption. Then it says there exists an element C in G2 and an isomorphism phi from G1 to G2, such that phi gamma 1 is conjugate to gamma 2. And then moreover, this measurable isomorphism per psi can be written as algebraically through this kind of phi G C gamma 2 for M1 almost everywhere G gamma 1 belongs to G1 modulo gamma 1. This is the isomorphic rigidity for unipotent flows. And I would like to say this result is very, very surprising. The reason is the following. We start from some measurable isomorphism per psi, which have no algebraic structure at all at the very beginning. And we all know that for measurable isomorphism, it even not necessarily preserve the dimension. We can construct many, many examples. However, if this measurable isomorphism is a measurable isomorphism between two unipotent flows, and the unipotent flows satisfies the previous slides, exactly this slide's assumption, which are very weak assumptions, then this measurable isomorphism, in fact, cannot be something arbitrary. It must be something actually induced from some algebraic isomorphism. And in fact, we know that we can show, in fact, from this theorem, we know that two groups are isomorphism, lattices are conjugate up to isomorphism, and two unipotent flows are exactly the same. So compare this result with the previous, this kind of Austin theory for the Bernoulli shifts. We should think about that the unipotent flows for the homogeneous dynamics should be understood as the Bernoulli shifts. In some sense, Bernoulli shifts for the positive entropy situation, which have both of these then have very, very strong features. In some sense. Okay, and in case that some of you, especially here we have some students, participants, so if are not familiar what is a unipotent flow. So here is a very simple picture to show you what is the unipotent flows. Here the green color is shows you what is a horocycle flow, and the red color is a geodesic flow. So geodesic flow and the horocycle, essentially geodesic flow always renormalize the horocycle flow, and so on and so forth. And the horocycle flow is the most simple unipotent flow on homogeneous space. Okay, once we have this result, let me briefly recall the history. So this result, in fact, was first established by Marina Ratner for horocycle flows in her 1982 annals paper. And that paper is not a long paper, but then that paper, I think it's around 20 pages. And in that paper, her idea of this kind of slow divergence or polynomial divergence, or later called as the R property or H property, is all essentially start from this kind of point, but not state explicitly. And later, she want to extend this type of the result to the product of the horocycle flows, which is the paper she published in 1983. And in that paper, she formally established the H property, or which is later called as R property. And by using Marina Ratner's idea in these papers, David Morris in 1985 and 1987 established the rigidity for zero entropy affine maps and translations. And Feldman and Austin extended this to the horocycle flows on variable negative curvature space. And Flaminio extended this result to the horospherical foliations or to compact manifolds of the constant negative curvatures. And David Morris, again, he extended this result to the horospherical foliations on some bundles other than the unit tangent bundle. And later, it's Flaminio and Spazier. They extended this result to the geometrically finite groups. And finally, it's in 1990, Marina obtained her famous result of the rigidity for unipotent flows as a corollary of the magic rigidity. I need to say that this rigidity of unipotent flows, in fact, was first established by David Morris in his 1985 and 1987 paper. And but if you all have the magic rigidity, by Marina Ratner, this will be a corollary, and this was written explicitly in her paper. Okay, so right now we have already talked about the rigidity, unipotent flows, and I haven't tell you the third key word of today's talk, which is a time change, because today's title is talk's title is time change rigidity. So right now, let me tell you what is a time change. So if we want to talk about time change, in fact, we need to start from the Kakutani equivalence, which is I like to say equivalent way to describe the time change.
Can I interject for a second? Can you go back to the history slide?
Yes.
So this horospherical foliation, what do you mean by, so here the equivalence is some sort of an equivalence between foliations?
Yes, I think it's more or less it's some geometrical, geometrical isomorphism. For the group, how to say, from the horos, if we have the isomorphism very weak, this kind of isomorphism from the foliations, they are, this is, I think you mentioned this Davidi's result, right?
Yeah, both Flaminio and
Flaminio and David.
Yeah,
Flaminio and David, they are very different or same in some sense, because Flaminio is basically still for the unit tangent bundle. And once we have unit tangent bundle, these kind of things, and you can define horospheral foliations, and then you can, if you have this isomorphism along these horospheral foliations, you are able to show them and isomorphism for this kind of manifolds, and that's what his target.
So I guess like once I mean they're using this Ratner results by thinking of this foliation as some sort of orbits or something.
It's not exactly use Ratner's result that easy. It needed to extend her result. It cannot directly activate her result because her result, I would like to say, based on my very naive understanding, Marina's result is major for the, I mean, majorly at that moment is for flow situation. And for the horospheral foliations, this kind of things, you need to adapt her technique and then obtain this kind of extensions.
Okay. Oh, thank you. I mean, that's, yeah.
Okay, thanks. Okay, so right now let's talk about the Kakutani equivalence. So as you can, if you still remember the isomorphism equivalence we have already mentioned at the very beginning. So this is just another kind of equivalence class, but I would like to say this is much weaker than the isomorphism equivalence relation. So if we have two flows, TT and ST, we say they are Kakutani equivalent, defined through this kind of FTT theta, I mean with capital K over theta to FT, if they are magically isomorphic to special flows over the same automorphism, which means that there exists as automorphism U and U function such that the F, which is the F1 and F2, which is the L1 positive function, such that the suspension flow UTF1 is isomorphic to TT, and the suspension flow UTF2 is isomorphic to ST. This is a Kakutani equivalence. And this is the original definition of Kakutani equivalence in his paper in 1943. And in fact, we can characterize this kind of Kakutani equivalence through the language of the time change. I mean, if you are familiar with the language of the suspension flow, of which is also called as special flow, this definition will be very straightforward. But if you are not familiar with the language of suspension flow, we'll provide you another option to think about the Kakutani equivalence, which is also very straightforward, which is called as time change. So what is a time change? That means, roughly speaking, a time change means that we have a dynamical system, I mean, which is a flow, and then we do not change the orbit structure, but we just change the speed of the system in a reasonable way. So more precisely, if for flow ST and alpha belongs to positive L1 function, the time change of ST is defined as ST alpha, which is a flow with the new speed function tau yt satisfies this and tau satisfies this integral equation. And once we have the definition of the time change, in fact, we can characterize the time change, the Kakutani equivalence, through the following language. The two flows are Kakutani equivalent through the Manpur psi if there exists alpha, which is the L1 positive function, such that TT is isomorphic, it's magical isomorphic ST alpha through psi. And we will say that tau is a time change cocycle corresponding to the Kakutani equivalence psi. So you see that through the language of the time change, we can characterize the Kakutani equivalence as something like two flows are magical isomorphic up to some time change. Then this means that they are equivalent, I mean, through the Kakutani equivalent. So this is another way to characterize this kind of Kakutani equivalence. And this is a rough picture. And if you remember the picture that I show you at the very beginning of the talk, please compare this picture with that picture, because this picture and that picture tells you the major difference between the isomorphic equivalence and the Kakutani equivalence. For this picture, you can say that if we send X to the psi X and through the Kakutani equivalence Manpur psi, right now, if we have the TT1X, it will send to some ST1 prime psi X. And for T1 prime, we do not know whether it's equal to T1 or less than T1 or larger than T1. The only thing we know is that T1 prime will large equal than 0. And for T2, TT2x, it will stand to some ST2 prime for psi x. For T2 prime, if we compare with T2 prime with T2, we also have no idea which one is larger. But the only thing we know is that T2 prime is definitely larger equal than T1 prime. Same thing for the remaining points. And as you can see from this picture, this demonstrates one of the most important features of the Kakutani equivalence. It preserves the order structure of the iterations. So namely, if we have a bunch of the points along one orbit, and its corresponding images after the Kakutani equivalence will exactly satisfy the same order. It will never break the order structure. And this is also the reason why that in the paper which is written by Anatoly Katok, he called this kind of equivalence relation as a monotone equivalence. This preserves the monotone structure. And some of you may wondering that what happens if we drop this monotone structure? Namely, if we let this alpha, we drop this kind of positive L1 condition just to request this L1. Well, if you drop this kind of monotone structure, this will quickly decay. This kind of relation, Kakutani equivalence relation will quickly become something which called as orbit equivalence. However, by Dice theory and later by Austin and Weiss result, all ergodic transformations and flows are orbit equivalent with each other. So from the ergodic theory point of view, if we only have orbit equivalence, it's not that interesting to talk about the transformations of flows. So in some sense, Kakutani equivalence should be understood as the weakest equivalence relation among, ergodic measure preserving flows, and which is better than orbit equivalence and much weaker than the isomorphic equivalence. Okay, let me talk about some features about this kind of Kakutani equivalence. I have already demonstrated this kind of the first point, which is preserves order on the orbits. And let's talk about the second thing, which is entropy class preserving. As I mentioned previously, for orbit equivalence, they are equivalent with each other. So we actually do not want this will be the same thing for the Kakutani equivalence. And that's in fact, this can be easily follows from the Aberov formula and the previous definition of this kind of suspension flow. By Aberov formula, we know that the entropy of the suspension flow is just decided by the entropy of the base transformation and the integration of this kind of suspension function, this root function. So by Aberov formula, we can easily know that the zero entropy system can only be Kakutani equivalent to zero entropy. Positive entropy can only be Kakutani equivalent to positive entropy, and the same thing to the infinite entropy. So this is entropy class preserving. So at least we know, Kakutani equivalence is not trivial among the transformations and the flows. And in fact, it's highly non-trivial. This is a result by Austin, Rudolph, and Weiss. They construct uncountably many pairwise, no Kakutani equivalent systems. And this is by cutting and stacking process, and this is a modification of the very famous Feldman example that, much early. Maybe not much early, I think it's 2 or 1 years early. But their construction is very classical. This construction gives you uncountably many pairwise no Kakutani equivalent systems, which in fact demonstrate this Kakutani equivalence relation is highly non-trivial. It's not just say that entropy class preserving, it's highly non-trivial. So that means if we are talking about the classification and many things among this kind of Kakutani equivalence relation, this is something reasonable. And once we have this kind of equivalent,
I had a question.
yes.
So just to be sure I understand the definition,
Mhm.
does it follow that all Bernoullis, all finite entropy Bernoullis are Kakutani equivalent?
Uh, I would like to say that in this kind of definition, as you can see, I majorly talk about the zero entropy systems. And in fact, we can define this kind of, I think we can define the losing Bernoulli, and which is a terminology I will mention immediately. I think we can define losing Bernoulli for positive entropy systems, and also this kind of Kakutani equivalence for positive entropy systems. But if we want to define that, we need to be a little bit more careful, because for zero entropy, this kind of systems, if we have defined losing Bernoulli and Kakutani equivalence, we only need to worry about one side. I mean, it's essentially, we only need to worry about the future. But if we define it through the positive entropy situation, we need to worry about the both past and the future. This was explained very clearly in the very famous Austin, Rudolph, and Weiss book. And so in this talk, for simplicity, all this kind of definition are directly adapted in the form of the zero entropy situation. Okay. Yeah, thanks. And in fact, the initial question is a very good question, because later I will mention something which called the losing Kronecker, which is exactly losing Bernoulli. And the reason it's called losing Bernoulli because it exactly try to mimic the feature of the Bernoulli in positive entropy in the zero entropy situation. And it's called zero entropy losing Bernoulli. Okay. Okay. Once we have this equivalence classes, it is a very nature question to think about how can we compare this kind of equivalence class? Is there a way, say that, which class, how to say, is in some sense, it's much more complicated, and which equivalence class is much more simple. In fact, there is such relation among different Kakutani equivalence class, which is called as majorization. So if we have two flows, TT and ST, I always assume that they are ergodic. So we say TT majorize ST if there exists an ergodic major preserving flow, UT, which is Kakutani equivalent to ST, such that ST is Kakutani equivalent to a measurable factor of the UT. This definition is a little bit involved. And let me mention why such definition is reasonable and makes sense. I believe that most of us are very familiar with the measurable factors in the isomorphic equivalence relation. So if ST is just a measurable factor of TT, in the definition, we just need to erase this UT and UT at all. Then it's just a definition of the measurable factor. But for Kakutani equivalence relation, we cannot directly say that, okay, if ST is a factor of some, it's a Kakutani equivalent to a factor of TT. That will lead to some counterexamples, and this kind of counterexamples of some very bad things was described explicitly in Austin, Rudolph, and Weiss book. I believe it's in chapter 4 or maybe chapter 3 at the very beginning. They mentioned this very explicitly. And that's the reason why in this definition majorization, we need to do essentially two Kakutani equivalence process. One is that we need to find a flow which is UT is Kakutani equivalent to FTT, and then ST is Kakutani equivalent to a measurable factor of the UT. Okay, right now we will mention one special equivalence class, and this is also the thing that when I answered the nation's question previously, which I called as zero entropy losing Bernoulli. So a system which is called losing Kronecker, if it's a Kakutani equivalent to a two-dimensional irrational flow. And here, I would like to say, this is definitely not the original definition of the losing Kronecker system. The original definition of the losing Kronecker system is much, much more complicated in some sense, or heuristic in some sense. But then if we want to define the losing Kronecker system, so that way that we need to do much, much more preparations. So that's the reason we chose this simple way. This way is very simple to describe, but In this way, we will miss a lot of the features of the loose synchronic flows. But for simplicity, let's temporarily accept that. And why this equivalence class is very special? Well, because by the result of the analytical talk and also Austin Rudolph Y simultaneously, I mean, we know that a flow is loose synchronic if and only if any ergodic measure preserving flow measures ST. In some sense, which means that loose synchronic equivalence class is a Kakutani equivalence class, has the least complexity among all equivalence classes. And later I will explain that, in fact, loose synchronic is the only obstruction to obtain the rigidity among all Kakutani equivalents for unipotent flows. Right now, let me briefly mention some features of loose synchronic and no loose synchronic, just in order to show you that loose synchronic is not just something as simple as something as a two-dimensional irrational flow. Loose synchronic, at first, it's closed under factors. And also, it's closed under inverse limits and the compact extensions, which means, in particular, all Neo systems are loose synchronic. And also finite rank systems, which means all translation flows, and then the horocycle flow. This is first a nature example, which constructed by Marina Ratner. And then it's some Gaussian systems, which is by Daren, and then the local rank 1, which is by Francis. These are all loose synchronic systems. Okay, so we know loose synchronic systems are quite broad quite general in some sense. And for no loose synchronic systems, we also have many examples. I mean, definitely the first example should go back to the Feldman, which is by Curtin and Stacking construct the no loose synchronic example. And then it's Austin, Rudolph, and Weiss for the uncountably many examples. And the first smooth no loose synchronic example was constructed by Anatoly Talk in 1977. And then it's the first nature example. It's constructed by Marina Ratner in 1979, which is a product of horocycle flows. And we will, in fact, mention this paper many times in today's talk later. And also, there is a zero entropy Verchik process, which is not loose synchronic, constructed by Rosten. And also, some Gaussian systems satisfy some condition by Daren. And together with Adam, we prove that product of projecting flows with different exponents is not loose synchronic. And Adam and Daren, they proved that product of two staircase rank 1 transformations are not loose synchronic. These are a bunch of the examples for loose synchronic and no loose synchronic. The reason I mention these examples is just to show you that both cases are quite broad and complicated. Right now, it's time to mention what is a time change rigidity for unipotent flows. And at first, let me briefly review the previous history results. The historical results along this line, the first result should go back to the Marina Ratner. She showed that all horocycle flows are loose synchronic, which in particular means horocycle flows are Kakutani equivalent with each other. Because they are loose synchronic, they are in the same equivalence class. So no rigidity can be expected at all. This is the first result. The second result is in her 1979 paper. She showed that product of the horocycle flow are not loose synchronic. This result shows at least we have some hope that in the product of horocycle flow situation, we may expect some rigidity. And in her 1986 and 1987 paper, Marina showed that rigidity of the time chain of horocycle flow with some regularity conditions on the time change. Namely, something like she put some Holder continuous condition for the time change rule function along this kind of SO2. And this in particular guarantee some, some faster decay relation for the ergodic averages, and hence she can expect it that for such time changes, she can obtain some rigidity result. And which means that if two horocycle flows are, time change isomorphic equivalent through such nice time changes, then their lattice must be conjugate with each other. This is for the regularity condition. And under the similar regularity conditions for the time changes, Siyuan Tang showed that the rigidity for the time changes to unipotent flows on SON1. And also on the same smooth time, under the same regularity assumption, and also with additional no convergence assumption, Artigani, Flaminio, and Ravati showed this kind of rigidity for smooth time changes for unipotent flows on connected semi-simple linear group for the general unipotent flows. But here there is a quite a technical assumption, which is a no convergence assumption for some certain, I like to say, major joinings. And such condition, I like to say, it's very crucial for their work. And I like to say, it's a condition. It's not easily dropped. And such condition can be dropped in the case that flow is a horocycle flow times identity. But however, in that case, I like to say the results is should be understood as kind of the extension of the Marina-Ratner's result for the horocycle flows. And so these are the historical results for the time changes for the unipotent flows. And I would also like to say, you can say for the 3, 4, 5, they should be understood as something like the time changes with regularity assumptions, and also with some other additional assumptions, such as this kind of no convergence assumption, which is some condition quite technical and very not easy to check, I would like to say. Yeah. Okay, so here is a question which is proposed by Marina in her 1994 ICM Zurich talk. So her first question is that if we have two flows, product of the horocycle flow, which is HT1 direct product with HT1 and HT2 direct product with HT2, which means not necessarily their lattice to be same, are they Kakutani equivalent with each other? So she's wondering in which situation to say for the product of horocycle flow is Kakutani equivalent to the product of the horocycle flow. The second thing is that are these isomorphism rigidity properties. Here she means that for her previous isomorphism rigidity results for isomorphism for equivalence unipotent flow, holding for the smoothly time change of the one parameter unipotent subgroups actions. The reason she asked this is because in her 1986 and 1987 paper, she can prove that this kind of results with regularity assumptions. And however, I would like to say in general situation, people cannot prove this kind of rigidity result only on the smoothly time changes. People may need some no convergence for the major journeys and so on and so forth. This kind of additional conditions. And our result, in fact, we fully answer these two questions without any regularity assumptions. So here is our result. So GI is the identity component of the real semi-simple algebraic group without compact vectors. And then all the other assumptions are exactly same as Marina-Ratner's result. Additionally, we need to specify this kind of SL2 triple through the Jacobi-Morozov theorem just for simplicity. In order to state this kind of our main result much more clear, which is we specify this SL2 triple and specify this kind of the geodesic flow, which renormalize this unipotent flows. Okay, here is our main result. If two unipotent flows are Kakutani equivalent, it's a dichotomy. Then either GI is just as simple as SL2I, as SL2R, direct product with GI prime, and the generator of the UTI of the both unipotent flows must be in the form that horocycle flow times identity. This is the first case. The second case is that there exists an isomorphism phi, which is a group isomorphism phi, from G1 to G2, and the element C in G2, such that phi gamma 1 is conjugate to gamma 2. Moreover, there exists S0 belongs to R, such that AS0 composed with psi is cohomologous to have an actual isomorphism, which means that AS0 psi G gamma 1 is equal to this kind of phi G C gamma 2 up to some composition of the UW G gamma 1, where this W is a horocycle satisfies this kind of horocycle equation. And some of you may wondering, why is this kind of expression for this kind of Kakutani equivalence in this kind of form is such a complicated thing? Because you see that Kakutani equivalence, we allow this kind of error terms or the perturbation along the orbit direction. Such items is something cannot be avoided at all. And in particular, if you go back to the Marina Ratner, her 1986 paper, you will see exactly the same expression for the isomorphism for the time change rigidity exactly should be in this form. Because in that case, for horocycle flow situation, we do not need to worry about many renormalization situations. So in her result situation, in some sense, this expression should be understood as the best expression can be expected among all these kind of Kakutani equivalence rigidities. So this is our main result. And why this result fully answers Marina's questions, 2 questions. For her first question, she is wondering, in which situation the product of the horocycle flows will be Kakutani equivalent to the product of horocycle flows? Our result, in fact, first answer this question, because the reason is that this kind of product of the horocycle flows is definitely not falling to the first case. Its generator is not in this kind of situation. And our result is a dichotomy, so it must be in the second situation. In the second situation, it tells us the group should be isomorphic. There's no problem for group because it's just a product of SL2R. And then it's a lattice. And our result tells us lattice should be isomorphic up to conjugation. So our result tells, as a corollary of our result, it tells us the product of the horocycle flows are Kakutani equivalent if and only if there exists an element C such that the lattice are conjugate up to this element C. Because if the 2 lattices are conjugated to this kind of elements, obviously they are isomorphic. So for sure they are Kakutani equivalent. And if they are only Kakutani equivalent, it follows from our result, the lattice must be conjugate. So this is the answer for problem 1. For her problem 2, she is wondering for this kind of isomorphic rigidity properties holding for smoothly time changes. Our main result directly answer this question without any regularity assumptions. So we do not assume any regularity for the time change function. We just need this to be a L1 time change. We do not need any holder or smooth condition for the time change function. So these are the corollaries. These are the corollaries and the remarks for our main result. The second result, the second corollary, or I would like to say another expression of our mean result, can be stated as the following. So people may wonder, is this the optimal result for the Kakutani equivalence rigidity? Say, can we expect some additional rigidity among the first case? The answer is no. The reason is it follows from our result together with Adam and Kurt previously. So in previous work, we show an ergodic unipotent flow UT of the G modular gamma is losing Kronecker if and only if G should equal its Lie algebra G should be in this form, and the corresponding unipotent flow is generated by this expression, which is exactly our first situation. So our mean result can be stated as the following. Under the same setting, if two flows are Kakutani equivalent and the one flow is not losing Kronecker, then there exists an isomorphism such that everything is fine. And in particular, if we request that our Kakutani equivalence is even Kakutani equivalence, which means that up to some renormalization of the geodesic element, then any even Kakutani equivalence between these systems are cohomologous to an actual group isomorphism. So this should be also another.
Even Kakutani equivalence?
Yeah, even Kakutani equivalence is just the Kakutani equivalence. Let me go back to the previous slides.
I must have missed it.
Yeah, even Kakutani equivalence is just for Kakutani equivalence, you additionally request that the integration of the alpha equal to 1. And in the case of the unipotent flow situation, you can easily renormalize any Kakutani equivalence to an even Kakutani equivalence by this geodesic element AS0. There definitely exists such S0, S0, such that after renormalization, your Kakutani equivalence becomes even Kakutani equivalence. Yeah. And even Kakutani equivalence historically plays a very, very important role in this kind of showing that, there exists uncountably many no Kakutani equivalent systems. Okay, so these are the corollaries. And here is another corollary I would like to mention. I will briefly mention it. So in 1980, Marina Ratner also created an invariant to evaluate the complexity among Kakutani equivalence classes quantitatively. So recall previously we have this measurization, which is qualitatively, it's just not specified, it's just a relation, but it's not providing any value. So inspired by this entropy construction, Marina created this entropy type invariant, which is called as Kakutani invariant. So if you are familiar with this entropy construction, essentially what you need to do is just define this F-bar metric and replace Hamming metric by F-bar metric in the construction of the entropy, and then you will have Kakutani invariant. But what is F-bar metric? I write many things here, and this seems very complicated. And I would like to skip these slides and use the next picture to explain to you what is the F-bar metric. This is F-bar metric. What is F-bar metric? We have the orbit of the 2 points, X and Y. We would like to match them. The Hamming metric essentially means we only allow the vertical match, and whether they are staying the same partition or not. But for the F-bar matching or F-bar metric, we allow these matching errors have some slope. Say the red part match to the red part, green match to the green, blue match to blue, and brown match to brown. We allow this kind of matching errors have some slope. However, we never allow these matching errors intersect with each other. Especially between the X and the Y. So they're not allowed to intersect with each other, but they are allowed to have some slope. This should be understood as a characterization of this seems very complicated, very complicated F-bar metric. But in fact, if you write this kind of things for the discrete situation, this will be much, much more straightforward. And the F-bar, in fact, follows from the I believe it's this first construct in the Feldman's paper. Yeah. But the continuous version was constructed in Marina Ratner's paper. Okay. The features for the F-bar metric is that once you have F-bar metric, you just follow the standard process to define the Kakutani invariant. And then instead of, even in the new numerator, you still take the logarithm for this kind of quantity, which is a minimum number of the F-bar balls of the radius epsilon with the time length r, need to cover the 1 minus epsilon portion of the space. And then by taking a generating partition and let epsilon goes to 0, you get this quantity. Why this quantity is important or interesting? Well, if this quantity satisfies this additional condition, which is UAT or UT goes to 1, and t goes to infinity for all a larger than 0, then two-system Kakutani equivalent implies the invariant should be safe. Okay. The second thing is that we have a way to compute. It satisfies this. If we only take value among generating partition, everything is fine. The third thing is much, much more important. A system is losing Kronecker if and only if this quantity is 0 for all these kind of scaling functions. So you see that based on this invariant, we have a way to distinguish whether two systems are Kakutani equivalent or not. If we pick scaling functions satisfy this condition, what is the nature candidate satisfy this condition? Well, if you take the u as a logarithm function, then log at is equal to log a plus log t, and it definitely satisfies this. And specifically for today's topic, because we are talking about unipotent flows, the complexity is in the polynomial scale. So the reasonable scaling function for UR selecting is definitely it's a logarithm function. So that's the reason Marina Ratner, using this kind of invariant, she showed that the horocycle flow are Kakutani. The products of the horocycle flows are Kakutani equivalent. The different products of the horocycle flows are not Kakutani equivalent with each other, unless they have the same coordinates. So then it's a nature question. For whether this invariant is a full invariant. If you still remember, at the very beginning, I mentioned this entropy for Bernoulli shift. So it's a nature question to ask whether for Bernoulli shift, whether for the unipotent, whether this kind of quantity is a full invariant or not, or in particular for unipotent flows. So together with Adam and Kurt, we show that this invariant at first is independent with the lattice, and it can be computed explicitly, and it has the explicit formula. And in 2021, Marlis Gerber and Philip Kohn, they obtained their breakthrough anti-classification results for Kakutani equivalence. They construct this kind of they obtain their anti-classification result by constructing very complicated systems on torus, and which is an analytic set, and which is not a barrier, and hence it's anti-classification. For the anti-classification, and in particular shows that Kakutani invariant is not a full invariant. However, their papers also ask whether Kakutani invariant is a full invariant for unipotent flows. And in fact, this is a very niche question, because unipotent flows is algebraic stuff, and in fact, people can expect many good things for algebraic stuff. But however, our result shows that this is not the case. So the reason is the following: just take the product of horocycle flow, and take two lattices, which are not isomorphic lattice. And then by the result with Adam and Kurt, we know they have same Kakutani invariant, because this invariant is independent of the lattice. But our result shows that they are not Kakutani equivalent, because they are Kakutani equivalent if and only if the two lattices are isomorphic with each other. So in particular, this means that Kakutani invariant is not a full invariant, even for the unipotent flows. So this is a corollary for this kind of things. So let me, so how many minutes do I have?
You have, sorry, Shilpanda, go ahead.
I think it's your choice, so you could.
Okay,
There is no
I'll speed
restriction
up.
here. Yeah,
Right. So it's like another 5 minutes to
Okay.
completion of an hour. But
Yeah,
then
5 minutes will be good.
but it's not a hard deadline. So
it's not a hard deadline. Yeah.
yeah.
Okay, thanks.
And since I unmuted, I would also ask, like, is there any other invariant talked about in this particular setup of the unipotent flows?
Oh, that's a very good question. So I like to say we also computed the slow entropy with Adam and Kurt previously for the unipotent flows. And that's the place where we begin to know that the unipotent flows are in the, in the polynomial scale, the complexity. And then Marina wondering what about the Kakutani equivalence for unipotent flows? And that's a project which we start after, we talk with Professor Anatolika talk, and then we begin to do this kind of Kakutani equivalence. But for something weaker than Kakutani equivalence, to be honest, I don't know, because for orbit equivalence, unipotent flows are orbit equivalent with each other.
No, actually, what I'm wondering is that, like, so this invariant is definitely not sufficient. It's not a complete invariant.
Yes,
that is clear from this corollary. But how far it is from a full anti-classification result? Like, do you believe that these are not classifiable, or do you want to add up some invariants and say they are?
That's something I don't know, because you see that the way that we answer this question is just as, I shouldn't say I don't know, but I would like to say, based on our result, it seems that because our result tells you the flow, if we have two unipotent flows, they are Kakutani equivalent. If and only if, especially if the group are isomorphic, if and only if lattices are conjugate with each other. So then it's a problem about the classification for the isomorphic lattice. So it's this, then it becomes job to our algebraic staff, based on my naive understanding. And if you are not allowed group to change, if you allow group to change, then it's much more complicated. It becomes to the classification of the isomorphic group. So group isomorphic, I think, should be fine. Then it's just
that should be fine. It's algebraic.
How many irreducible lattice among a given group, and the cardinality of the irreducible lattice gives you the cardinality of the Kakutani occurrence for unipotent flows.
Okay.
Yeah.
Okay.
Okay. So let me very briefly mention the key ideas. In the case of the toy case, which is the product of horocycle flows. So in the toy case, we will, I believe most of us are very familiar with this Bowen ball, because we all have experience to address some certain, I like to say, problems in the entropy category. And here we need some terminology, which is a modification of the Bowen ball, which is a Kakutani Bowen ball, which is a Kakutani, and which is something like we do some renormalization in the SL2 triple and along this orbit direction. So one major problem, or one major lemma, one key lemma for our project is that we establish that up to Kakutani equivalence, the Kakutani ball will be sent to the Kakutani ball. If we ignore all this kind of quantification, just essentially tells you that exists a good number and a good set such that everything is fine. So it tells you if X, Y in good set and R is large enough, then if X is in the Kakutani Bowen ball of the Y, it will be also stay in the Kakutani Bowen ball of the psi Y up to some delta. And the most important part of this result is that R was sent to the R, the same exponent. The proof of this lemma was built on the ideas of the Marina Rotten's 1979 paper and also the result with Adam and Kurt. In 1979 Marina's paper, she obtained this type of result by direct computation. The computation is amazing in her paper, but it's very complicated. And she also needs many additional assumptions for the lattice, but the computation is really amazing. And in our previous result, unfortunately, we cannot do the same exponent. We have here is r, and here is some r with power 1 minus eta with eta larger than 0. But that weak version will be enough for us to deduce the number of the invariant. But the weak version is not enough to obtain the rigidity. So this is the first improvement. This improvement is that we replace our previous multi-scale analysis by the direct error estimates through some algebraic features. This is the first key lemma. The second key lemma is that we would like to understand what happens of the Kakutani equivalence up to some renormalization of the geodesic flow of the geodesic element A1. Why we would like to think about this? If you write down on the sketch paper, simply you will see that if you think about this guy, A minus n psi t at an, if you let n goes to infinity, and if you're able to show the limit of this guy exists, you will see that the limit of this guy will be exactly a measurable isomorphism between unipotent flows. So if the limit of this guy exists, you can quickly reduce all the problems from Kakutani equivalence to the measurable isomorphism. That's the reason why people always study this kind of things. And this is, in fact, at least based on my very naive knowledge from the Marina's 1986 paper. And in our result, we are able to show up to some correction in the centralizer, not in the orbit direction, in centralizer of the orbit direction, except not in the orbit direction directly. The error term, there's no error terms at all. Say, the only error terms will be in the orbit direction. It's in the UT. And this is very nice. This essentially means we do not need to worry about the existence of other error terms. However, this is still very dangerous, because if we would like to think about such a limit, this amount, we have no bound at all. This t can be very large. And by ergodic theory, by ergodic theory, we can only bound this t. For, say, if we are talking about this kind of things, we are only able to bound this t for large portion of the ANX. There always exists some bad time moments. So exactly as you can see in this picture, this green points means that the t, the corresponding t here is bounded. The black point means that the corresponding t is unbounded. So this means that we cannot deduce the existence of this limit easily only from the previous lemma. So we need something else. We cannot do the iteration among this part. That's the reason we need the following L2 ergodic theorem. This is also a result, in our paper. So together with Professor Lindenstrauss, we have the following result. So there should be a unitary representation of the SL2R of the Hilbert space with no fixed vectors and also a spectral gap. So then there exists epsilon 1 less than 0, such that the following result holds. So we have the following decay. Why we need the following decay? Because as a direct corollary of this L2 ergodic theory, we have the following corollary. In particular, this means in the case that without compact factors, because without compact factors will guarantee the existence of the spectral gap. For any f belongs to L2 and almost everywhere x belongs to G mod and gamma, we have the following limit exists. And if you are familiar with homogeneous dynamics, if you are able to request that f is something like the smooth C1, C2 function, this result is trivial. Then it just follows from the Margulis famous banana trick. However, in the case that f has no regularity, something like L2 function, this is not trivial. This, in fact, indeed needed the previous result. And why this result is good for us? Because this result tells us that in this B epsilon H, in this very, very small ball, we can always find a good set. So we can always find a good point. Say, for example, you can let f be a characteristic function of the good set. In particular, that means if we're very unlucky, we have this bad point, we are able to find a very good point in its neighborhood in the B epsilon H ball around this bad point. And then we will do the iteration along this point. Although if we do the iteration along this point, we will have some additional error terms. But these additional error terms can be addressed nicely through our first K-lambda. And then we are able to address these additional error terms. And in particular, this will guarantee that the limit will exist. And once the limit exists, then the question can be reduced to the measurable isomorphism between unipotent flows. And hence, we are there, and we would be very happy. And that's everything, and thanks for that. Thanks for error, and sorry for a little bit overtime.
Thanks a lot, Shilpak. Sorry, thanks a lot. I wanted to say thanks a lot, Shilpak, for bringing in Daren, but either way, thanks to both of you.
Thanks.
Great talk. Let's thank the speaker.
Thank you.
So, questions?
So I have kept on asking questions. So I just am curious, like, are you still thinking on something after this on this line, or?
So for this kind of questions, we have, I like to say, for this type of the results, we expected something like I like to say, much, for this kind of result, let me go to the mean result. This mean, if we're only talking about the unipotent flows, this line, I would like to say, is is done. There's nothing can be done for unipotent
Yeah, that's
flows. Yeah. And if you are talking about unipotent actions, say, for example, in high ranks, and we are doing something like with Adam, Kurt, and Philip. And this is an ongoing project.
Okay, and I'm curious also about this no compact factor. So I'm not very familiar. So
this is a very nice question. So without compact factors, this is a very typical assumption to guarantee that you will definitely have a spectral gap for your corresponding unitary representations. So let me go to here.
Yeah, that's what I said. Yeah, here.
Here. This, in fact, is the only place where we need the spectral gap. Because the spectral gap is mainly for that we want to isolate some certain representations. And because if you think about the unitary representations, you have the discrete and mock discrete principle and the continuous, this kind of part. And this spectral gap mainly makes sure that for the continuous reducible representation, you have a gap there. And it's not too close. It depends on whether the way you give them the coefficients, whether it's stay away from 0 or stay away from 1. This gap will guarantee that you will have this kind of decay, because this decay will in particular guarantee this kind of series will be bounded. And however, in the homogeneous dynamics situation, a very nature condition to guarantee that without a spectral gap, with a spectral gap, is that without compact factors. And in this way, by the historical literature, say the work by Dubé-Clammer and Peter Sarnak, and then Margulis and Kleinbock, and many others, with this kind of condition without compact factors, we can easily obtain that corresponding SR2R has a spectral gap. And this, in fact, is the only place that in our project we use the without combined factors.
Okay. So I guess
Other questions? Okay. Thanks, Daren, again.
Okay, thanks.
okay.
Thanks a
Thank
lot
you,
for
Daren.
the